IMFs day one. We are going to be looking at, for the next couple of days, we'll be looking at liquids, solids, and solutions and their properties. So how do we identify from a molecule what types of forces are going on there? Why are they in the particular phase that they're in? And everything that goes along with that. So give me just a second here to set up a couple of things and we will get moving with this lecture. All right, so I'm going to move kind of quickly through this material as I don't want this to be too long of a video, primarily recording this from my AP Chem 2 class so that they can um, go through their in-class problems if they miss class or if they just want to review. So looking at this first side, intramolecular forces or intermolecular forces. Big idea here is that we need to pay attention to what the word is saying. Intramolecular means within the molecule, inside the molecule. So most of the time in the past we have referred to these as bonds, or specifically chemical bonds. All right. These are our true bonds, chemical bonds. This is a chemical process, very, very strong bonds. All right. Moving on to intermolecular forces they occur between the molecules. These are not bonds. They are definitely not chemical bonds. These are forces, usually electrostatic forces, due to a positive and negative or temporary positive and negative attraction between certain molecules and certain atoms. Just kind of giving you, there are three main types of intermolecular forces: dipole-dipole forces, hydrogen bonding, and again, even though it says bonding here, not a bond. Want to make sure that we are clear on that. And then London dispersion forces. So dipole-dipole and hydrogen bonding are what's called, they are classified, you might also hear these as van der Waals forces. And just so that you know, these typically occur in polar compounds, polar covalent. And understand that intermolecular forces are always going to happen in covalently bonded compounds. Intermolecular forces do not occur in ionic bonds. Ionic bonds form ionic bonds. All right. So van der Waals, dipole-dipole, and hydrogen bonding, these are the strongest IMFs. However, keep in mind that IMFs are only like 1% as strong as a chemical bond. All right, talking about London dispersion forces, these occur in everything. These are the weakest. Weakest type, but this is also the only type of force, or the only force that we see in non-polar molecules. All right. I'm going to go into more details in the slides that follow. So just make sure that you kind of pay attention as we go along. All right, so intramolecular bonds are stronger than intermolecular bonds. So know that a chemical bond is always going to be stronger than an intermolecular bond. Let's just go ahead and kind of move through the slides. Um, so this next slide that we're looking at, we are looking at um, a water molecule or several water molecules. What I want you to realize here is, just looking at the distinction between an intramolecular bond, where this is our intramolecular bond versus an intermolecular force. Um, this is the actual bond between oxygen and hydrogen. And then these little dots right here are the IMF. Now, a water molecule will have hydrogen bonding that occurs, and the hydrogen bonding occurs because of the electronegativity difference between oxygen and hydrogen. That oxygen is one of the highest electronegative elements, so the electrons are going to spend a lot more time around the oxygen than it is the hydrogen, causing a partial positive on the hydrogen end and a partial negative on the oxygen end, causing this huge dipole moment that occurs through the water molecule, causing it to be very polar. So on AP-like question that you might see has happened in the past, that they have a question, true or false, water molecules break bonds as they change phases. Well, that is false, because no bonds are broken during a phase change. What does happen is intermolecular forces are overcome. Specifically, the hydrogen bonds, which again are not bonds, they're intermolecular force, it's a dipole-dipole attraction, is overcome. So as we add energy to the solid water, the ice, the molecules begin to vibrate a little bit more, and as that vibration becomes more and more exaggerated, then it is easier to overcome the hydrogen attraction, the hydrogen and oxygen attraction there, the positive negative attraction. So we move from a rigid solid to a flowing liquid, and then as more energy is added, eventually the molecules become pretty much free of the intermolecular force, and they're free to bounce around as a gas. So no bonds are broken, only IMFs are overcome. Moving right along. So this is just an example of a heating curve. We talked about this in class on Wednesday. Just make sure you kind of know what's going on here, that energy is being added or heat's being added at a constant rate and temperature is increasing, or as we're decreasing temperature, we see that energy moves the other way. Pay attention to the length of the amount of time that it takes, or the amount of energy that needs to be added here versus here, and what's being done at this point as well. All right, just another example. This is a triple point graph. We will talk more about these later in the unit. So let's go ahead and address the forces. We're going to go from the weakest to the strongest and hit on these concepts. So thing I want you to know about London dispersion forces. Well, the first thing is that London dispersion forces exist in all molecules. I also want you to know that these are the weakest of all the IMFs, and that since they are the weakest and they do exist in all covalent molecules, the thing that we need to realize is that we're only going to really recognize them in nonpolar molecules. The reason why is because nothing else is going on in nonpolar. Um, so if we take chlorine gas, bromine, and iodine, and we look at these, and when we look at the periodic table, we see a trend that chlorine exists as a gas, bromine exists as a liquid, and iodine exists as a solid. Well, why does this happen? It happens because of IMFs. The IMFs are increasing in strength as we move down the periodic table. Well, why does this happen? Well, what's changing about these? The number of electrons. Okay, so well, how does that matter? Why does that matter? Well, in chlorine, we have um, we have fewer electrons than we do in iodine. So what this does is that as we increase the number of electrons, we increase this opportunity to create what's called an instantaneous dipole. Um, so we have our iodine bonded with iodine here, and we have all of these electrons floating around with it. And what we have is this chance of creating this partial negative side and partial positive side um, as a temporary dipole because of the electrons concentrating more on this end for a very brief time, and then that'll affect another molecule causing the same thing to happen, and they all line up. And so they create this instantaneous dipole due to polarization. And that's a big deal. So when this happens, you create these temporary or instantaneous dipoles. The molecules line up for a brief period of time, and then all of a sudden it shifts the other way. So, and this happens in all molecules, but it's only really noticeable in the nonpolar molecules. All right, so let's go to the next one, dipole-dipole. Dipole-dipole will occur in polar molecules. The big thing I want you to kind of look at here is realize that London dispersion forces, I said this earlier, but they're only about 1% as strong as a covalent or an ionic bond. These dipole-dipole occur because of that dipole moment that we have a molecule that has a dipole. So if we look at the compound CH3Cl. All right, so if we look at this structurally, carbon's in the middle, we have our chlorine, and then we have our hydrogens. Well, what we know is overall we're going to have partial positive charge on this end, partial negative charge on this end, so we're going to have this dipole moment that's moving this way through the molecule. So when this interacts with other molecules, the dipoles are going to line up. The negative N will line up with the positive N, and so forth. And we'll see that happen over and over again. And this is much stronger than a London dispersion force. And so even though there are London dispersion forces, the electrons can shift throughout the whole molecule. Um, we're gonna see the stronger dipole-dipole interaction. All right. And so another type of dipole-dipole force is specifically called hydrogen bonding. Again, not a bond. Make sure that you are clear on this when you're writing your responses and when you're discussing these type of equations. It's not a bond, it's just misnamed as a bond. All right, so hydrogen bond occurs when you have a hydrogen bound to a highly electronegative atom. So what are highly electronegative atoms? Nitrogen, oxygen, and fluorine. So we have to have hydrogen bonded to one of these threes. So if you see a compound that has a covalent compound that has an OH attached to it, like an alcohol, or water, H2O, is going to form hydrogen bonds. Hydrogen fluoride, those type of things will form these types of bonds, and this is the strongest of all the IMFs. All right, so let's look at this on a graph or a chart. So looking at your notes real quick and looking through your in-class problems, let's go ahead and look at this chart and let's just identify some things about it. So let's take this yellow line, the top line first. So we have H2O, H2S, H2SE, and H2TE. All of these are going to form a bent molecule. So you got the H's back here, and the and whatever molecule you have right here. All right. So what's going on? Why is the boiling point so much higher for water than hydrogen sulfide? Well, water undergoes H bonds, hydrogen bonds. But what type of intermolecular force is happening with these three molecules? Same shape, still polar, but we don't have this great electronegativity difference in these three. So these are all dipole-dipole. Now, we should also note that we see this trend that as we increase the number of electrons in the molecule, we see this trend that the boiling point starts to increase again. So why are these increasing? Well, these are increasing because London dispersion increases, and it increases because of polarizability. All right, makes sense? Good. So this increases because you have the interaction of dipole-dipole and London dispersion happening. This one is so high because of the hydrogen bonds. Notice that we have hydrogen fluoride and ammonia that are very high boiling points as well because the hydrogen bonds are occurring in those. Now let's look at this line at the bottom. What's going on here? Why are the boiling points so low in these? Well, because all of these are non-polar molecules. And what type of IMF did we say occurs in non-polar? These are all solely dependent on London dispersion. So we're dependent on this temporary dipole or instantaneous dipole due to its polariz, polariz, polarizability. I can't say that word. Um, so let's go ahead and move forward and talk about a couple of things. These next two slides are just information for you to be able to read on your own. If you go in the in-class problems, spend some time with that. These are coming from the Pogles. It's just description of each of the types of intermolecular forces. And again, you can read those on your own. Now, let's go ahead and look at some problems like we would do with this type of material. So let me move some stuff around so that I can have some space to write and everything is nice and neat and clear. You have plenty of room on your in-class problems to write these. All right, so I'm going to go ahead and expand this just a little bit so that we can see and do this. So this is an example of an AP style question that you might be asked about intermolecular forces. Which molecule is capable of forming stronger intermolecular forces? N2 or H2O? Well, let's go ahead. What do these look like? So N2 is going to be nitrogen triple bonded nitrogen, and we got these nice little lone pair electrons on the outside. And then we have H2O, so we have our oxygen, hydrogen, and our hydrogen makes this nice little bent molecule, and we have our lone pairs on that side. Well, what do we know about this one? This one has a dipole moment, so it is polar. It'll be a polar molecule. This is a non-polar due to the symmetrical arrangement of electrons in this, or the even distribution of electrons. So this is a non-polar molecule. All right. So which one will form stronger intermolecular forces? H2O. Now, how do we explain this? We need to make sure that as we're explaining this, we explain this from the perspective of both molecules. So I would say something like, All right, so I would say something like this. H2O will have stronger intermolecular forces because it is a polar molecule that has H bonds in the as far as the IMFs. And N2 is nonpolar, and it will only experience the weaker London dispersion forces between the molecules. All right, so let's look at the second part of this question, or the second question here. Draw two Lewis structures for the formula C2H6O. All right, so you need to recall what an isomer is for this. Remember that an isomer is something that has the same chemical compound but completely different structures. So we would have these two structures for this C2H6. So and then the other version would be CO. All right, so what are the difference between these two? Well, you should remember from organic that this is an alcohol and this is an ether. All right, so draw two Lewis structures for the formula C2H6O and compare the boiling points between the two molecules. Well, what's going to make a difference in the boiling point? Um, the difference in the boiling point is the stronger IMFs in the molecule, the higher the boiling point. So what do we know about this one? Well, looking at it, it's got this nice symmetry. It's got this nice distribution of electronic charges. So this one is a nonpolar molecule. And then this one, we have this OH group on here. So this one's going to have some hydrogen bonds as far as its London dispersion forces. So that means it's going to have this nice little dipole running through it. All right, so that means that this one is going to be a polar molecule. So which one will have the higher boiling point? The alcohol. Higher boiling point. Now, a couple of things to remember about this one and a couple of things just to note. Over here on the ether, this one is volatile. Basically, it's going to have a very, very low boiling point. In fact, this one will sublimate, turn to a gas very quickly. And, we associate these things like with chloroform and other anesthetics that will knock you out and things like that. All right, we're going to do one more problem, and then that is it for today. So let's go ahead, look at this last concept check. Which gas would behave more ideally at the same conditions? So we need to remember ideal gas law. So if you remember, PV equals nRT. Now, when we take the ideal gas law and we adjust for real gas behavior, we need to remember that um, pressure in the real world decreases because of IMFs between the molecules. You know, the particles don't just bounce around freely without experiencing any attraction for each other. And then we also have to remember that volume is changed because the smaller the particle or the larger the particle will affect the, so particle size impacts the volume. So we're going to be looking for two things. We're going to be looking for small IMFs and small particles. So the smaller the particle, the smaller the IMF, the more ideal it's going to behave. All right, so when we're looking at this one, which one will form, which one of these two molecules will behave more ideally? All right, so when we look at this, we have carbon monoxide, CO, double bond, and then we have N triple bond N. All right, so mass-wise, we have carbon at 12 and oxygen at 16, so 12 plus 16 gives us 28, and nitrogen 14 plus 14 gives us 28. So particle size, we're kind of negligible here, but what we can look at is that this is going to be a polar molecule, and this is going to be a nonpolar. So which one is going to have the less effect of IMFs? Well, this one only experiences London dispersion, whereas this one will experience dipole-dipole. So N2 is going to behave more ideally. Because of smaller IMFs. That concludes our lesson for today. Please watch the video and make a comment.